So as you're using these tools, remember that you need to understand whether they're rack aware or not, so that it can help you at the lower level and it can help you at the higher level. Now, when you tune rack, you have to tune it as an entire system or as a whole. And this really goes back to what Jeremy said, which is if you know carry milsap and the method R technique, one of the big things is understanding where your database is spending its time, or more importantly, not the database, but where the user is spending time. If the user has a 30-second wait time, but it only takes 1 second to occur in the database, then the database is not the problem. And sometimes with rack, because there are so many complex or moving parts, part of the problem is making sure that you're truly identifying which piece of the pie is contributing to the problem. It could be the public network is overworked. I was in a shop once where we had everybody on a single segment, and so we were getting collisions on our network, and once we split into multiple segments, it fixed the problem. Same with your private network. I've had people who accidentally put their private network on a public network and then wondered why the interconnect was slow. And finally, your storage. You know, it has a network. And have you multipath? Do you have enough HBAs? Do you have sufficient switches and the right type of switches for your HBAs? And are you using the right type of storage? A lot of times you can look at this picture, and using method R, you can put a circle around your instance or your cluster and say, it's not me. And sometimes that's the most important part of this battle. Likewise, Jeremy mentioned some things to do that are kind of generic. One of the things I've noticed is that when you use ASM, and ASM is great, I'm not saying anything negative about it, but the default parameter, which is like 64 megs for the memory, is way too small, especially if you have more than 2 nodes. So definitely when you set up your ASM, you do want to increase the ASM memory allocation. I found that anywhere between 128 and 256, depending on the number of nodes you have. Next slide, please. I just wanted to reiterate that the rack performance is the sum of its parts. And what I mean is, because there are these multiple moving parts, you have to look at all of them. And as Jeremy mentioned, there was the top-down and bottom-up, and what I'll kind of call the traditional focus for the DBA. And now we have to ask ourselves additional questions like the storage network, the public network, and again, back to the application nature. We're going to press on that application nature in a few moments. But all of these items are critical when you look at the system as a whole. So on the prior slide where we saw that it's a complex system, you have to look at the sum of all the parts in the system. And again, using the method R, where am I spending the most time in that complex system? And it could very well be outside of the database. Next slide. Now, I only show this picture. I do a lot of proof of concept works down at the Dell labs, working with some of the people at Dell and their customers. And I only wanted to show this in that this is the first thing I always draw when I work with rack, is I make myself a picture. And in this picture I see I have 10 nodes, and I know that I have multiple fiber switches, and I know what types and what the performance characteristics are. I know what kind of Ethernet switch I have, and whether it supports virtual LANs or VLANs, or whether I'm separating private and public networks by having physical switches to separate them. And then I also have my storage arrays and understanding how many heads I have and how many caches per head. This picture a lot of times is important to going back to that prior complex system picture and saying, okay, the user said there's 30 seconds delay. Where could that be occurring? So a lot of times this is an important component to have when you're trying to troubleshoot your rack, which is what does my rack subsystems look like and how are they interconnected so that I can truly find where the bottleneck is. Next slide, please. Okay. A lot of people like to start out with the wait events and getting into really deep detail, like which wait events should I be looking for, and what is different at a very detailed level, rack versus single instance. And what I find is most of the times if you start first with a configuration checklist, you can eliminate a lot of the problems that you'll have. For example, and we mentioned this in our first presentation, all the nodes should have similar performance characteristics. If 3 of my nodes have quad cores and 1 of my nodes has a single core, that node could become a bottleneck, especially if that node ever gets picked to be the master. Then everyone else is slowed down by his performance. So again, now I'm not saying they have to be identical, because sometimes you're given a machine and it's not exactly the same. But as long as they're in the same performance class, that's pretty good. Now the interconnect in rack is really the Achilles heel. I know that we just mentioned a few slides ago that it's CPU and I/O as well. But what I'm trying to get at is there was an old joke a long time ago. I'm probably dating myself. You know, the Cray computer, the Cray supercomputer was so fast it could run an infinite loop in 4 seconds. Well, that might be true, but you know, we all realize that that's a false assumption. In other words, there's a weakest link, and no matter how fast everything is, it can only run as fast as the weakest link. And a lot of times, the interconnect is a good place to start. Is it truly on its own private segment? Have I bonded together NICs to improve the throughput? Are all the nodes and all of the NICs on those nodes set to use jumbo frames? And are my switches, and if I set up VLANs on my switches, have those been set up to use jumbo frames, and have they all been set up to use the same size jumbo frames? And finally, we're in an age now where we can consider 10 gigabit Ethernet for the interconnect, and actually, you know, for the $600 a card it costs, you know, that's sort of a no-brainer for my customers. I pretty much tell them, you know, get the 10 gigabit. Now the storage, we want to have multipath. Some people will be using InfiniBand. If you're using iSCSI, you might be doing 10 gigabit Ethernet. So there's some things here that you would treat the same. One of the things I find that people sometimes don't look at, and I think we mentioned this on an earlier slide, is that for my storage array, knowing how its firmware is set to handle, so not just at the LUN level, but also all the way down into the firmware. A lot of times you'll find that a lot of disk arrays are set up to do 80% read and 20% write caching, or just the opposite. If I'm doing OLTP, I might prefer it one way, and if I'm doing data warehousing, I might prefer it the other. And sometimes just knowing how that's set up can make a huge difference. Then finally on the software, obviously all the nodes ought to have the same OS patches and the same Oracle patches. Oracle recommends and really pushes for using ASM on rack. I do on occasion still use clustered file systems, but there's literally no good reason not to use ASM anymore. It offers a lot of advantages. And don't rely on non-rack enabled scripts or tools. For example, if I'm only using StatsPack, and it may help me tune each of the instances, but it may not help me spot the problem for the entire complex system in a cluster. So when you do buy tools, or when you do choose to use tools, you're going to want to have some that are rack aware or rack cognizant. Otherwise, you might miss a problem at a high level, and that goes back to my thing about, you know, the infinite loop in 4 seconds. If there's a fundamental problem on the interconnect and your StatsPack doesn't tell you that, no matter what you tune with StatsPack, your interconnect is still the problem. And as Kerry Millsap always tells you with Method R, you know, you can tune something that takes 2% of the time, but it's the one that takes 70% of the time that is where you should be spending your time. Next slide, please. Some things that are important as well. The database configuration assistant with Oracle has a default block size of 8K. There's nothing fundamentally wrong with that. And a lot of DBAs out there have experienced over the years that bigger block sizes are better. It used to be that smaller block sizes were better, and over the years, over the last, let's say, 10 or 15 years, you know, we've moved from people doing 2 and 4K blocks to pretty much just always doing an 8K block. But bigger is not always better. You remember Jeremy had a slide a few slides ago that said we ought to find a way to decrease the number of rows that are in a block. Well, one of the ways to do that is to have a smaller block size. So you have to think about the block size and also the number of nodes. We'll talk about that in a few slides here. Because no matter how fast or good cache fusion is, if you stress it or push it artificially, it can buckle, or it can become truly the Achilles heels. So we don't want to force the interconnect to rise to the surface. We want to make sure we do things to keep the interconnect on an even par with other items. Now, let's say that we had an OLTP application using an 8K block size and having 8 nodes. That larger block size would mean more rows per block. More rows per block would mean more likelihood of block contention. I'll show you what that means in a moment. And more nodes, especially when you're bigger than a 4-node cluster, also improves that likelihood of block contention. If you start getting a lot of block contention, what will happen is you're going to be asking cache fusion to potentially do a lot more work. And remember, the interconnect, or where cache fusion occurs, can often become an Achilles heel. So let's look at the next slide. Let's say that I'm in my single instance database and I have 2 different Oracle processes. And one of those processes wants to do some operation on row X, and the other database process wants to do some operation on row Y. And row X and row Y, as you can see, are both in the same block. There is information stored at the end of the header. That's why I've kind of highlighted that bottom right corner of the header section. There is information stored there to tell these processes whether row X and row Y are locked or not. So in this case here, there's no contention. Even though we're both doing things in the same block, we're doing it on different rows. It's only when those 2 processes in a single instance want to go for the same row that there would be row contention. Next slide, please. Now, let's take that same picture and put it into a rack environment. Now, the 2 red arrows at the bottom are there for if you're still doing OPS, which I think Tariq talked about earlier, which was in the old days, before cache fusion, operations where we had to move a block and copy it from one node to another would do that via the disk, or would at least have disk writes involved as part of the migration process or the synchronization process. So let's take the same picture we had before. The first process wants row X, and that block happens to be in node number 1's SGA. And the second process, which got load balanced over to the other node, he wants row Y. And we know from earlier that row X and row Y are in the same block. Therefore, we're going to be asking cache fusion, hey, potentially there could be, depending on the transaction nature and the current status of the blocks, we could be very well asking or forcing cache fusion to do that synchronization right there for that block, since we have 2 processes trying to get to different rows but on the same block. And the point is, as the size of the block gets bigger, the likelihood of having a row Z, for example, that would also be a problem, increases. And likewise, as I start adding more and more nodes to the cluster, again, now I've got another case where now I've got a 3rd or a 4th or a 5th Oracle process that gets load balanced to another node. And now I might have to start sharing that information across multiple nodes. And then finally, remember, I think it was Syed that said it way up in the beginning, that cache fusion is not always a single node-to-node or 2-node hop. Sometimes it actually has to go to a 3-node because one of the nodes will be acting as the master, and the cache fusion will actually go to the master and then to the node. So it will go source to master to target. So you have to think about these things, because I've actually gone into customers that had too large a block size, and they're sitting there trying to play with all the possible wait events. And I know it seems like a real pain in the butt, but all we did was switch their block size, and we got almost a 30% improvement in their rack performance. So sometimes, while we may want to start at the bottom and work up, we first have to make sure that we don't have any poor decisions in that top-down. Otherwise, we'll be wasting our time in that bottoms-up. And that's why I kind of started with this information. Next slide. So, yeah, that's true. To summarize, and Tariq, do you want to do the summary?